Yes. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you for coming. Here I will explain about chapter 7. This is our last chapter in Physics 1. Chapter 7 will talk about fluids. Involve two main topic, fluids statics or statica fluida and fluid dynamics or bahasa dinamika fluida. Yeah. And in our previous meeting, I have attached some video from Professor Matt Anderson, and you can, I think you already has learning asynchronously from the video. The first topic that we will talk about this morning is about the pressure underwater. And I think you have watched from the video. If there is a fluid, you can see in this video about the pressure underwater. And in this video, Prof. Matt Anderson
Hello class, Professor Anderson.
to explain about the pressure, use the definition of Bernoulli equation. You can see from the screen. Wait a minute. Okay, you can see from this equation. This equation based on the Bernoullis equation. And instead of using Bernoulli equation, I will explain how to derive the pressure underwater by this configuration. Okay. If we have a fluid, large fluid like this one, in some compartment, and then I will make a small part of the fluid. For example, I will change the color. I will take just this part. And on the top of the water or fluid has the pressure of atmosphere. This is 1 atmosphere. This is the pressure of atmosphere. And in Pascal, you can convert into 10 to the 5 Pascal. Okay. And usually we denote the pressure for the atmospheric pressure as P naught, P0 or P naught. Okay. Now we continue to this element. For example, like this one. The problem is what is the pressure? The pressure in this point. Okay. And now, firstly, please consider about the P naught here on the top of fluids. This P naught, and then in the bottom of the part of the fluid is P. And the characteristic of pressure is can press any surface of the fluid, of course, also in this element. Yeah. The direction of the pressure on the top is downward, and the direction of the pressure at the bottom is upward. And then in each point on of the element also exerted the pressure like this P1, and this also P1 in around the element, and in different weight also exerted by P2, and P2 is of course exert on the same height around the surface. This P2, and also before reach the bottom, for example Pn, around the element also have the pressure of Pn. And the important understanding here, we have to remember that this pressure is cancel each other. The pressure around the element here, around the element here, in all the surface is P is cancelled each other. So just two pressure remaining. The pressure at the bottom and on the top. So maybe I will make drawing again. For example, like this. This P not, this P. Okay. So just there are two pressure, P not and P. Okay. And now in this fluid, this element have the weight of mg, mass times gravity. Now I think you have understand what is the force on the top and at the bottom. The fluid undergone by force at the top as F naught. And at the bottom, the fluid experience the force of F. Okay, and F naught is P naught times A, because the definition of P is F over A. Okay, and then F, of course, F is P times A. Now we can apply the first law of Newton, because the fluid is not moving anywhere, and the fluid is not moving anywhere, so we can apply sigma F equals 0. And then F minus F naught minus mg equals 0. Okay. And we can apply the definition of pressure, because F is P times A, and we have this one is P, and then A minus P naught A, and then we can change the variable of M to be rho times V. V is volume, because the density of the fluid can be defined as rho. Rho is the density of the fluid. Rho equals mass over volume. And then volume can be changed into A times H, the surface times the height of the element. This is the height of the element. Now we can make the further calculation. P, and then this one A. I will continue in this part. P A minus B A minus P not A minus rho, and then V can be changed into A times 8. This is rho. Okay, now by eliminate A, because in every sum has the variable A, we can eliminate A, and we have P equals atmosphere pressure plus rho I'm sorry, M is rho V. This there is a G here, the gravity. So this one is rho G IH. Okay, this is the other derivation how to obtain the pressure under water instead of using Bernoullis equation. Because in the physics 1 you will learn about the Bernoullis equation in fluid dynamics later. Okay. Any question, everyone?
Not yet, sir.
Okay. And I think I will move the video into the last, and we also have the same result. That's the same result from the video. This is the P. Okay, this is P and equals P naught plus rho G H.
And they really won't hurt all the way.
Now we'll move to Archimedes principle. The Archimedes principle is in the topic of fluid static or statica fluida. Okay. In Archimedes principle, you will have the understanding about the object in the water. Is the object float or sink? Okay. And you can see from the video
Sink if it's made up of other materials like metal.
and from the Archimedes principle. For example, there is a fluid. There is a fluid again like this, and then there's an object. There's an object, and the object has a weight of m times g. If the object located in the water will have a buoyant force. This buoyant force. Yeah. Buoyant force in bahasa Indonesia is gaya angkat, gaya angkat ke atas. This buoyant force, and the buoyant force is from the sigma F equals 0. The buoyant force will be mg. Okay, and m can be converted into rho times volume g. Okay, Please wait a minute. I will charge my notebook.
Let's talk about fluids. So this can be.
Now, please pay your attention by looking this video. From the derivation in the video, we get the buoyant force is rho GV or rho VG. Yeah. The buoyant force is rho V. V is volume, G. And from this note, buoyant force equals weight of displaced fluid. Yeah. Buoyant force equals the weight of displaced fluid. Ya, jadi gaya angkat ke atas atau gaya Archimedes itu sama dengan berat, ya, berat dari fluida yang dipindahkan. Ya, berat dari fluida yang dipindahkan. Furthermore, because the depend on the weight of the fluid, so M here can be expressed as rho is the volume G. This is the water, rho water, and the volume of water that displaced. Yeah. If the mg, the mg large than the pion, so the object will be sink. Yeah. From the video, you can obtain the understanding that the object will be sink if the weight larger than the pion. And float when mg less than the pion. Okay. And please see the video. This is the rho. This is the density. Okay. And if we talk about the weight of the plate's fluid, rho here is the rho of water. Please wait for the video. Now you can compare the two variables P, M, and G. Yeah. To define if the object sink or float, you can see from the video here to how to calculate P greater than mg or less than mg. Because the pion here depend on the displaced water, so in this part, rho belongs to the water, H2O or W is water, and this one is G and the volume displaced, volume yang dipindahkan. And is the rho of the object, okay, or rho O, and then G and the volume. Okay, the volume of the object is the same as the volume of the displaced water, so we can eliminate this part. And the indicator of sink or float you can find just from the density. If the density of the water greater than the density of the object, it will be sink. Oh, I'm sorry. If the raw water greater than the density of the object will float. And vice versa. If the raw water less than the raw object, the object will be sink. Okay. Any question, everyone?
Not yet, sir.
Okay, thank you. And I can write if the row of water less than row of object, the object will be sink. Okay, now we move to the next topic.
Density of the box.
Yes? Any question? Now we move to Archimedes Principle. Oh, I'm sorry. This is not Archimedes Principle. Please wait, I will change the type. I will retype the subtopic. I think we have to move to Bernoullis equation before we learn about the hydraulic lift. This Bernoulli, the Bernoullis equation. The detailed derivation, you should watch the video in your classroom about the Bernoullis equation. Okay, I just give the point in this lecture. The Bernoullis equation is derived from this configuration. If there is a fluid moving from the bottom to the top, and the fluid is incompressible. Incompressible means the density here that have the large section area, and this the smaller section area, then density is not changing, or the density is the same. If the water have the density of rho here, rho water, and in when fluid enrich the top part here, the density is still the same. The density is still rho water. This is the definition of fluid. Here is incompressible. Okay. And by using the definition of works and the conservation of energy from the conservation of energy, you will find the Bernoullis equation in the form of P1 plus rho G H1 plus half rho V1 square equals P2 plus rho G H2 plus half rho V2 square. Okay, this for the 2 point in point at point 1 and at point 2. This is the very important and beneficial equation. Now you can understand this is the mathematical expression of the flowing water. Okay. As I mentioned before, we have to transform the characteristic of or behavior of the universe into mathematics before we can manage or harness the universe. Okay, you have to understand the language of universe by mathematics. If we do not convert the behavior into mathematics, I think we just apply the water for the shower or take a bath. But if we can convert the water into the mathematics, we can get the valuable formula. And this is the result of we consider about the water deeply. Okay, this equation can be applied to design the wings of the flight plane of the plane. Yeah. This is the design of the plane. Yeah. To lift the plane, so we have to design the wing to have the buoyance. Ya, memiliki gaya angkat. Ya, the buoyance. We can lift the plane if there is a buoyance to the top or upward. To reach this buoyance, so on the top of wing, the pressure has to be smaller than the bottom. And to obtain this condition, the wing has to be designed. The velocity on the top has to greater than from the bottom, greater from the bottom. Okay. This is because from the Bernoulli equation, P plus rho sorry, I will run the slide again. I will ignore this. And from the Bernoulli equation, we have P plus rho GH plus half rho V square is constant. Okay. So to reach the P smaller, we have to increase the velocity. Yeah. Because the sum of this term is constant. And then the consequences of this, if we want to small the pressure, we have to increase the velocity. In other words, if we want to reduce the pressure, we have to raise the velocity. Okay? And the result is the plane have the buoyance upwards. Ya. Pesawat bisa mendapat gaya angkat ke atas. Ya. Tidak hanya gaya dorong. Gaya dorong itu harus diubah menjadi gaya angkat dengan with the design of the wing. Okay, this is the Bernoulli equation. Now, the other application of Bernoulli's equation is the hydraulic lift. Okay. You can learn from the video, and I will not rewrite again the derivation, but you will have this one, this equation. Because there is open tank here, left and right, we will have F1 over the area 1 equals F2 and A2. And from the diagram, from the figure of the video, you can lift the much heavier object on the right by using just small force apply into the left side. Okay. For example, this one. So by using the much small force, you can lift the much larger of object.
The idea is the following. To this is a big piston, and then there is a little.
Now from the video you can also not only the small F1 can lift heavy object, but also you can derive the diameter of D1 needed to lift the object on the right side that have diameter 2. D1 equals the square root of m p m epsilon d2. A here is for elephant and P is person, yeah. P is person, E is for elephant. Yeah, elephant. Hopefully the writing is correct. Elephant, gajah in bahasa Indonesia. Elephant. Any question, everyone?
Not yet, sir.
Okay. Now we move to Torricelli. Torricelli's tube. Tabung Torricelli. Ya. Tabung atau tank ya, tabung aja ya. Torricelli tube. Nah, coba dilihat di buku. Is it tube or tank? Yeah. Because the case is like this one. There is a large tube or tank that contain water. Yeah. And at the bottom of the tank, we make a little hole here. Okay, we make a little hole so the water can flow through the little hole. For example, this is a table. I'm sorry, I will replay the slide. The question is, what is the velocity of the water comes out from the little hole here? Yeah. And we can approach by using the area between the larger area on the top. For example, this one is E naught because the pressure here is P naught, and then this one is A. The section area is A. The small hole have the section area of A. Now we can apply the Bernoullis equation. P plus rho G H1 plus rho V 2. Sorry, not 2 but 1. Yeah. Rho V square equals P naught plus rho G H naught plus half rho V naught square. Oh, sorry, I forgot to explain about the continuity. Yeah. The continuity of fluid. Yeah. If we have the different area here, A1, and then this one is A2, and then the velocity here is V1 and this one is V2. You can apply the continuity equation as A1 V1 equals A2 V2. This is the continuity. Sorry. Continuity. A1 V1 A2 V2. V here is the velocity, not the volume. This is the velocity. Small v is velocity, yeah, and capital V is volume. Now we can apply E naught V naught equals A V. And we can say here V naught depend on A equals A naught V. And if we apply this velocity into this V naught square, we have the A over A naught square. We have this this part A over A naught square, and we know in this configuration A naught is much larger than A. So if we apply in this equation A over A naught, the value or the result will be approach 0, because the small value, if we square, the value will be smaller and smaller. and the result will approach zero. Okay? And the consequences of this part is also approach zero. And we can rearrange the Bernoulli equation into in this one, because there is a small hole here, and the water is connecting to the atmosphere here, so the pressure also have P here is equals to P atmosphere, yeah. P naught or P atmosphere. And we can eliminate this part. Okay. Now, please look this configuration. If from the base on the bottom, this one is, for example, this one is H, ya. Ini ketinggian dari sini, ini adalah H from the bottom, and then from the hole to the ground, for example, it's not, and if we denote the H minus is not as the delta H, yeah. But you can also, for example, the symbol is not H and H naught, but this one is P1, H1, this is V1, yeah, this V1, H1, and this A1, A1, so P1 equals P naught is 1 atmosphere. This, for example, H1, and the heat here this, for example, H can be determined by H1 minus H naught, yeah. And from this expression and from the what we get before, we can understand, or you can rearrange and also eliminate rho, because P1 equals P naught, and then rho you can eliminate, and we have just the expression V1 equals the square root of 2 GH is the simple expression. Any question, everyone?
Not yet, sir.
Okay. So the important thing is H here is the different height between H1 and H0, ya. Jadi H di sini adalah selisih tinggi antara H1 dan H0. Ya. Jadi ini adalah tingginya yang menentukan di persamaan bawah itu. Ini adalah H Okay, everyone. In the next meeting, we will talk about Venturi tube and the rest of topics. Yeah. Or maybe yes, in the next topic you will learn about the Venturi, or maybe you will have the assistant is, I think is the assistant is complete. So the two remaining meeting I will give you the other topics and also problem and solution and also other example. Okay, everyone, thank you for coming. See you next Tuesday. Thank you very much. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Thank you, sir.
wabarakatuh.
Thank you, sir.